Well, okay. So it's nearly 10 o'clock. I'm pleased to introduce the first speaker this morning, Magdalena Musat from the University of Copenhagen, who will speak on the Connes-Kirchberg problem, quantum correlations, and infinite dimensional phenomena in quantum information theory. Official starting time is 2 seconds. Please go ahead, although I presume it's afternoon there.
It is 4 o'clock in the afternoon, and thanks a lot. I did not know that you were my chair, so that's a nice discovery. And in fact, I'm very happy to be part of this conference. Thanks a lot to the organizers, Ilias and Brad. And regretfully, we had to cancel our physical participation last minute. So thanks also for kindly accommodating my participation online. This is really special. Yeah, so we'll try very much to listen to the talks presented and try to stay in touch with the topics. Yeah, unfortunately via email. So what I would like to talk about is the Connes embedding problem via an analysis of. So it's a survey of the Connes embedding problem via an analysis of sets of correlations that have also revealed some interesting infinite dimensional phenomena in quantum information theory. And then fundamental work of Kirchberg that has led to the name I have for my talk, the Connes-Kirchberg problem. And towards the end of my talk, maybe discuss some recent developments in the analysis of quantum correlations, most notably so the so-called synchronous correlations. So I'll start my slide talk. I hope it functions. On my screen, it keeps going, so that seems to be okay. Right, so 1976, in his celebrated Annals of Mathematics paper, Alan Connes formulated the following question: is it the case that every 2-1 von Neumann factor admit an embedding into the hyperfinite, into an ultrapower of the hyperfinite 2-1 factor R? Roughly, this amounts to asking whether any 2-1 von Neumann factor approximately embeds into a matrix algebra. And I very much like the title that Rona Raiza and Rolando de Santiago found for their survey paper they put in Notices of AMS in 2016. And I bring this up all the time again. Are we living in the matrix? So the Connes embedding problem amounts, Smiling is saying, are we living in the matrix? Now, embeddings of a 2-1 factor M into an ultrapower of the hyperfinite 2-1 are precisely characterized by result of Kirchberg from his fundamental paper, Invenciones paper from 1993. And here it is, a 2-1 factor M embeds an embedding into R omega if and only if for any small tolerance epsilon and any set of unitaries, say U1 through UN in capital M, one can find a size K and unitaries, matrix unitaries of size K, such that the correlations or second order mixed moments or correlations of the initial unitaries U1 through UN can be approximated or replicated within the given tolerance epsilon by correlations or second order mixed moments of the matrix unitaries V1 through Vn. So that's precisely what an embedding of M into R omega amounts to. Now, in view of the theorem, it's natural to consider the following sets, and my top of the screen is covered by this banner, so maybe I'll try to move it to the bottom.
We can see it. Just consider the following sets of n by n matrices, etc.
Okay, you can see it. That's good. All right. So consider the following 3 sets consisting of n by n matrices whose entries are correlations, second order mixed moments, and they are decorated by script G, and increasingly so additional decorations. So one is G matrix, the other one is G fin, and the last, the most general one, no decoration. So G matrix consists of all n by n matrices whose entries are second-order mixed moments of unitaries coming from matrix algebras of arbitrary sizes. Then we have G-fin, where the unitaries come from arbitrary finite-dimensional sister algebras, and the most general ones, the unitaries come from arbitrary 2-1 von Neumann factors. These sets, G matrix, G-fin, Gn, are included one into each other. They are all equal in dimension 2. And related sets, one can consider, maybe it's the same thing, yes, these where the unitaries are replaced by projections. So we have D matrix inside D-fin inside D of n. As a consequence of Kirchberg's theorem that I just mentioned, one obtains a reformulation of the Connes embedding problem as follows. It has a positive answer if and only if the set G of n is the closure of G matrix in all dimensions n greater or equal to 3. Now, I want to point out that G of n is closed always for every n. And in order for this to make sense, one should put the closure operator on operation on G matrix, because a priori there is no reason to believe that G matrix is closed. So for good measure, we put the closure. I put it in red. And in fact, it took a little bit of a while to settle this problem. Do we need this closure or not? And that came in a result with Michael from 2019, where we showed that, in fact, G matrix is not closed for any n greater or equal to 3, and neither is it convex, while G-fin is convex in all dimensions, but it's not closed whenever n is greater or equal to 11. We don't know what happens for smaller n's. The method of proof doesn't give it. And I'll tell you where this number 11 comes from. So what we employed to settle these results was what we called a trick. So this was communicated to us by William Slofstra in the spring of 2018. And these are ideas of his together with Oded Regev and Thomas Vidic. And this is our formulation of their ideas. As follows. So if you have a von Neumann algebra M, tracial von Neumann algebra, and n projections P1 through Pn in it, one can naturally associate to them 2n plus 1 unitaries. The first one is the identity. The next n are symmetries obtained out of the given projections. And the last n of them are unitaries that one constructs by a standard recipe out of these symmetries, U1 up through UN. So n projections given, associate 2n plus 1 unitaries like this. Then if n is another von Neumann algebra with normal faithful tracial state, one can find 2n plus 1 unitaries in this von Neumann algebra capital N, replicating precisely the correlations of the unitaries UIs, if and only if one can find n projections in this von Neumann algebra N, replicating precisely the correlations of the original n projections P1 through Pn. It's a bit of a mouthful when you read it, but it's actually a very simple idea that's behind it, namely that if one takes the map that takes unitary uj to unitary vj and extends it linearly between their spans viewed as Euclidean spaces when equipped with the inner product given by the traces, then this map is an isometry. So that's responsible for the conclusion. We call it a trick because in many ways it's very simple, but it does a lot. So it's a trick. It's a powerful trick because as a corollary, when read it appropriately, it yields the fact that if you have a matrix of correlations of projections, which is in the closure of D-fin, but not in D-fin itself, then the corresponding 2n plus 1 unitaries associated as above to these projections P1 through Pn will have the property that their matrix of correlations, it's in the closure of G-fin in dimension 2n plus 1, but not in G-fin itself. So in other words, if we know that D-fin in dimension n is not closed, we obtain that G-fin in dimension 2n plus 1 is not closed as well. So the heart of the matter for the result for the result with Michael would be to prove that D-fin is not closed. As far as the closure of G matrix, this is taken care of the fact that the set D matrix in dimension n is not closed for n greater or equal to 1, because this set is rationally convex, but it's not convex. If we look at an arbitrary matrix belonging to this set D matrix, it has on the main diagonal traces of projections, therefore rational numbers. So that's how it goes. And then apply the trick. So what one has to show after all, it's that the set D-fin in dimension n is not closed for n greater or equal to 5 to obtain all the results I said before. And for that, in fact, we did follow the arguments of Dijkema, Paulsen, and Prakash from their paper in 2017. 2017. But we streamlined that proof in the sense that we stayed completely within techniques from operator theory. So let me give you a glimpse of the idea. If sigma n denotes the set of all positive alphas for which there exist n projections on a Hilbert space, adding up to alpha times the identity, then it is known that this set sigma n consists entirely of rational numbers when n is less than or equal to 4. What happens for n greater or equal to 5, it's covered by this beautiful result of Krugliak, Rabanovich, and Samoilenko from 2002 that Dijkema, Paulsen, and Prakash discovered and brought to play. Namely, this result says that there exists n projections on a finite dimensional Hilbert space, adding up to alpha times the identity on H, if and only if this alpha belongs to sigma n and is rational. And furthermore, the following interval is entirely contained in the set sigma n. So using this theorem, together with Michael, we show the following. We are in dimension n greater or equal to 5 and take a t in this interval here, which is chosen in such a way that n times t will lie in sigma n. By the way, note that the requirement that n greater or equal to 5 ensures that this square root makes sense. And now define a matrix, n by n matrix, depending on t and n, to have t on the main diagonal and constant entry on the off diagonal given by the number written there. As soon as t is irrational, this matrix will belong to the closure of D-fin, but not D-fin itself, attesting to the fact that D-fin in dimension n is not closed. So then, as I explained, tracking back things, this leads to non-closure of G-fin in dimensions 2 times 5 plus 1, which is 11, and the other things. Now, I'd like to quickly mention an application of this result. So that led to reveal some infinite dimensional phenomena in quantum information theory. So for the next 2 slides, I'll take you to the world of quantum information theory. I recall that a quantum channel is a completely positive trace-preserving map on the n by n matrices, at least for me. We are particularly interested in a certain class of quantum channels, so-called factorizable ones, and I'd like to propose that we take the following, which is actually a theorem. We take it for a definition. So such a channel, so a channel T on in dimension n, it's factorizable if there exists another Von-Neumann algebra with a normal faithful tracial state called the ancilla and the unitary in the n by n matrices over n, such that T has the following representation. It resembles a lot the Stein-Spring dilation theorem, but it isn't, as we shall see. So very easy examples are automorphisms of the n by n matrices. So these are unitarily implemented channels. And in fact, in dimension 2, every quantum channel is a convex combination of unitarily implemented channels, automorphisms of the 2 by 2 matrices. This is Kumara's result from 83. This statement fails in every dimension greater or equal to 3. That's a statement that so-called quantum Birkhoff conjecture fails for n greater or equal to 3. Other examples of factorizable channels are the so-called completely depolarizing ones. They take an n by n matrix and output a scalar multiple of the identity n by n matrix by means of the normalized trace of x. Some people call that completely randomizing channel. And more interesting class of examples exhibited by Rick Ricard in 2008. These are sure products associated to real correlation matrices. Factorizable channels in dimension n form a nice set. They are convex and closed and greater or equal to 2. And they are not all channels in dimension n. So in every dimension greater or equal to 3, there exists non-factorizable ones. We provided examples with Uffe in 2011, and later on, together with Beth Ruskay, we have a recipe for producing lots and lots of examples, systematic recipe for producing examples in every dimension greater or equal to 3. The interesting thing about them is that every such non-factorizable channel is a counterexample to an attempt to restore the quantum Birkhoff conjecture in the asymptotic limit due to Smolin, Verstraete, and Winter from 2005. In this way, the class of factorizable, respectively non-factorizable channels gained some interest in the world of quantum information. Therefore, the question whether do we need infinite dimensional von Neumann algebras to describe factorizable channels was not just an abstract question that we were interested in. Somehow it became a little bit more interesting to a larger community, the quantum information community as well. It's not an easy question to answer because I can say right away that given a factorizable channel, even simple examples of such like the completely depolarizing ones, exhibiting or deciding if there is a minimal size for an ancilla is difficult. So for the completely depolarizing channel, possible ancillas are c to the n squared. So this is commutative, finite dimensional. The n by n matrices over C, so non-commutative yet finite dimensional, but also a very infinite dimensional object, corner of the reduced free product von Neumann algebra of 2 copies of Mn. So not easy to answer the question. But we did attempt to answer this together with Uffe and trying to understand the class of the factorizable channels admitting a finite dimensional ancilla, which I'm denoting here by FM decorated with fin, led to connections to Connes-embedding problem. So this is the result with Uffe that we had. So Connes-embedding has a positive answer if and only if the set of factorizable channels with the finite dimensional ancilla is dense in all factorizable channels for all n greater or equal to 3. So for example, if we knew that every factorizable channel does admit finite dimensional ancilla, we would have an answer to the Connes-embedding in the positive. We couldn't settle this with Uffe, but the answer, in fact, came based on this non-closure results for the sets of correlations that I showed you before. And then we could indeed prove that factorizable channels with finite dimensional ancilla is not closed. This set is not closed whenever n greater or equal to 11 is the same 11 of before. And in each such dimension, one can find factorizable channels which do require type 2-1 ancillas. So infinite dimensions have a place in quantum information theory and need to be taken into account. So the idea behind this theorem, how does it connect to the previous results I showed you? It connects via the fact that if one looks at Schur multipliers, factorizability of them, so Schur multiplier associated to some matrix B, factorizability of that amounts to knowing that B is a matrix of correlations of unitaries coming from a 2-1 factor. So B belongs to G of n. And in this correspondence, admitting a finite dimensional ancilla corresponds to this matrix B being the matrix of correlations of unitaries coming from a finite dimensional C-star algebra. So that's the correspondence. So once we showed that G fin is not closed in dimension greater or equal to 11, it leads to this. Now, maybe because this is an operator algebra audience, I want to emphasize that factorizability, in fact, is a notion that has been introduced in a larger context. In the context of non-commutative harmonic analysis, it's a notion that Claire de la Roche introduced in 2005. Maybe, in fact, in an even larger context than the one I'm presenting here, but this is enough for making the point of the actual definition of factorizability. So let's say that M with phi is a phenomenon algebra with normal faithful tracial state. A unital, completely positive phi-preserving map on M was called by Claire factorizable if there exists another phenomenon algebra with normal faithful tracial state, so-called an ancilla, such that T really factors through, has a factorization. It's a very rigid one, and it's a factorization via a star homomorphism, injective star homomorphism, which preserve the states phi and psi. And the actual factorization is achieved using the adjoint of beta appropriately defined in this setting. So it is an actual factorization. So what I showed you before, it's more of a special characterization in the setting of M being matrix algebra. Turns out that the notion of factorizability—
What is beta star?
The adjoint of beta in this category, the adjoint of beta. Yeah. So in the setting when M is the n by n matrices, beta has really a very precise form. So that helps with realizing it in the way I showed before. But in general, it's just the adjoint of beta. So the factorization is beta star composed with alpha. So the notion of factorizability is the same as admitting a dilation in the sense of Kummerer, introduced in this more general setting by him in 1985. And I want to bring up some updates on this whole setup. Charles Duquet defended his PhD thesis in July, and I was member of the PhD committee. So he wrote his thesis in Besançon under Christian Lemerdy. And in his thesis, he introduces and studies a notion of absolute dilation in the non-normalized tracial setting. So versus this dilation notion, which was studied before. And they can show that if T on M is absolutely dilatable, then T extends to a positive contraction on LP of M, admitting an isometric P dilation. This should be viewed as a non-commutative Acoglu-Sukeston dilation theorem. And for those of you in the audience that are very much into ergodic theory, you may recall that the classical Acoglu-Sukeston dilation theorem had very interesting applications in ergodic theory. So hopefully this non-commutative version of it will provide many interesting consequences in the non-commutative harmonic analysis realm. And furthermore, in his thesis, Charles studies absolute dilatability notion and applications.
Sorry to interrupt. What is P?
Yeah.
What is P?
For every P between 1 and infinity. For every P. So on LP, for every P between 1 and infinity. So that's actually what Acoglu-Sukeston dilation theorem was about in the classical setting. So this should be viewed as a non-commutative analog of it. Yeah, sorry, I was too quick in writing these slides. So thank you. For every P between 1 and infinity. Okay, so there is a larger realm for looking at factorizability. So it's really an interesting notion. Now I'd like to take you back to the setting of quantum information and to the setting of factorizability for channels, where factorizability was governed by this formula or representation for the channel as you wish. So these are factorizable completely positive maps on the n by n matrices. And what we discovered with Michael is that factorizable channels can be parametrized using the simplex of tracial states on a very nice sister algebra, the unital free product sister algebra of 2 copies of Mn and n by n matrices. So it goes as follows: if one has a tracial state on Mn free product Mn, one gets out of it a n squared by n squared matrix, with entries described by this formula here in the center. This matrix is positive, therefore is the Choi matrix of some completely positive linear map on the n-by-n matrices, which, small turn of luck, turns out to be a factorizable quantum channel. And in fact, this correspondence that takes a tracial state on Mn free product Mn to the associated factorizable channel via this recipe described here is an affine continuous surjection, which is going to take tracial states that factor through finite dimensional C-star algebras to precisely factorizable channels admitting a finite dimensional ancilla. And continuity of this map ensures that phi takes the closure of T-fin to the closure of the factorizable channels admitting a finite dimensional ancilla. So at this moment, I bring up again the results with Uffe that I showed you before, connecting the closure of the factorizable with finite dimensional ancilla being all the factorizable channels to the Connes embedding problem having a positive answer. So it's natural, therefore, to ask, what can we say about the closure of T-fin of Mn free product Mn? Do we understand this better? Can we understand this better? So this C-star algebra, Mn free product Mn, has nice properties. It's residually finite dimensional, RFD for short. So it has plenty of finite dimensional irreducible representations. It's a nice result of excellent Loring from 92. And Bruce Blackadar showed in 85 that it's semi-projective. Therefore, it has nice, very good lifting properties. And using all this, we could show with Michael that the closure of T-fin is all hyperlinear traces on Mn free product Mn. So hyperlinear traces, that is traces for which the associated phenomenon algebra in a GNS representation embeds into R omega. So the closure of T-fin takes us all the way to hyperlinear traces on Mn free product Mn. As a corollary, it follows that the Connes embedding problem has a positive answer if and only if all traces on this C-star algebra, Mn free product Mn, are hyperlinear for all n greater or equal to 3. The way we proved this corollary is via this theorem we had with Uffe, and then all these connections between factorizable channels and the trace simplex. But in fact, this corollary can be obtained directly, as it was suggested to us by Jesse Peterson. So we also wrote down that proof. And ideas that Jesse communicated to us will also be useful later when I'm going to show you another result of the same kind. So this corollary can be proven without appealing to connections to factorizability, this corollary here. Okay, so now Michael had been interested for a while in understanding quotients, what are possible quotients of Mn free product Mn. So we set further to analyze that, and we could show the following things written here, that Mn, the n-by-n matrices over some unital C-star algebra is a quotient of this free product. If that happens, then A is generated by n squared elements. Respectively, if A is generated by n-1 unitaries, then n-by-n matrices over A is a quotient of Mn free product Mn. And then using further a result that was proven by Hannes Thiel in his diploma thesis with Wilhelm Winter, unital separable Z-stable C-star algebras are singly generated, led us to concluding that if A is a simple unital infinite dimensional AF algebra, then the n-by-n matrices over A is a quotient of this unital free product C-star algebra of 2 copies of Mn, so Mn free product Mn. Now, building of results of Lazar and Lindenstrauss from 71, Goodall proved in 76 that any metrizable Choquet simplex is the trace simplex or arises as the trace simplex of some simple infinite-dimensional unital AF algebra. I want to thank Bruce Blackadar for the precise reference. I used to quote something else before. Putting together all these things here above, we could show that every metrizable Choquet simplex is affinely homeomorphic to a face of the trace simplex of Mn free product Mn for every n greater or equal to 3. Our methods don't say anything about n equals to 2, so we don't know what happens for n equals to 2. And I also want to point out that for a Choquet simplex, for a metrizable Choquet simplex, to have this property that every metrizable Choquet simplex can be realized as a face of it, this is a necessary condition to get a Paulson simplex. A Paulson simplex, the Paulson simplex distinguishes itself among metrizable Choquet simplices as having the set of extreme points being dense. But this condition of having every metrizable Choquet simplex as a face of it, it's necessary but not sufficient for obtaining the Paulson simplex. There is a homogeneity condition that additionally needs to be satisfied. That homogeneity condition we could not settle, so therefore we left the question whether the trace simplex of Mn free product Mn being the Paulson simplex open. So I have some very recent news about that. It's actually an archive posting of precisely a week ago, August 21, a preprint of Orovitz, Slatsky, and Viktorovich. We had a previous version of this preprint via personal communication, but then somehow the communication got interrupted and no posting on the archive. And so I wish to thank Ilan Hirschberg for restoring this communication. They wrote to us. And in fact, they posted a new version of this preprint saying that the answer is yes for n greater or equal to 4. They believe that the answer is yes for n equals to 3 as well, but the methods of proof don't give it. So the answer is yes. The trace simplex of Mn free product Mn is the Paulson simplex. It's a very nice paper, I have to say. We have not absorbed yet all the very interesting results they prove in it. So one further very interesting result they prove in it is that another realization of the Paulson simplex is the trace simplex of C star, the full group C star algebra of the free group, on n generators for n between 2 and infinity, including 2, including infinity. This is a very interesting result because it says that every trace on the free group is a pointwise limit of characters, and this is a strong negation of character rigidity. So there are many interesting results in this paper, and I'd like to advertise it. It's a very nice paper. So we have an answer to this now. And for the last part of my talk, I'd like to take you back to quantum information analysis of sets of quantum correlations this time, leading to connections to the Connes-embedding problem, the fundamental work, the fundamental contribution of Kirchberg, leading to the title Connes-Kirchberg Problem, and also to report on some recent developments in the analysis of quantum correlations, namely the synchronous ones. So the way I like to view quantum correlations is arising via measurements. So in the somehow context of the Einstein-Podolsky-Rosen paradox and the notion of entanglement. Producing quantum correlations is the setup of Alice and Bob, two scientists residing in spatially separated labs, and each receives part of a quantum system on which they can perform measurements. What they measure are, so the observables are self-adjoint operators on Hilbert space, and what they measure is eigenvalues of these self-adjoint operators corresponding to an eigenvector which describes the state of the system. So the states are vector states. So more concretely, Alice and Bob can measure any one of n possible observables, each of them with k possible outcomes, and we are interested in understanding probabilities, namely probability that Alice gets outcome A when measuring observable X, and Bob gets outcome B when measuring observable Y. These probabilities can be modeled in various ways. Mathematically, one is the classical model, according to which there exists a probability space consisting of hidden variables that are yet to be discovered in a more accurate model. That's the theory of Einstein, Podolsky, and Rosen. But then there are also these quantum models, in fact, two of them, the tensor product model and the commutativity of observable models, in which one has, for the tensor product, one has two Hilbert spaces, one belonging to Alice, one belonging to Bob. The vector, the state of the system is described by a unit vector in the tensor product of the two Hilbert spaces. In the commutativity of observable model, there is a common Hilbert space, and the unit vector belongs to it. And what the two scientists have at their disposal in this quantum setting is additionally a projection valued measure. So these are k-tuples of projections adding up to the identity. So I will not describe carefully what's written on these slides. I think many people know them, but I will bring you to the next slide where I have put together these sets. These are convex sets of nk by nk matrices with real entries. And these are the sets of quantum correlations in respectively the classical model, so C calligraphic or script C sub C, the classical model, and then the two quantum models, spatial tensor product, respectively the commuting of observables model. So they're pretty self-talking for themselves, what's in them. And also to say that when restricting to just finite dimensional Hilbert spaces, one has somehow possibly smaller sets of quantum correlations, and they are decorated with fin at the top in the quantum setting. Now, this box that appears here presents the relationship between these sets, these convex sets. So I'm going to look at the bottom of the diagram. So there are clearly at least as many correlations in the quantum world as there are in the classical setting. In fact, I'm going to mention on the next slides that there are strictly more correlations in the quantum world than in the classical setting. And then the commutativity of observables model allows for more, so it includes the spatial model as well. And they are all sitting in the nk by nk matrices over the real line. I will explain in the next slide that QC, so commutativity of observable models, produces a set which is closed already. As far as the QS spatial setting, it's not clear a priori whether this set is closed or not. So we interpose between these two the closure of it. I'll talk about it on the next slide. And what else do I want to say? For the top of this diagram, when we restrict to finite dimensional Hilbert spaces being used, bringing this fin decoration at the top, Cyrilson proved in the 80s that in this setting, finite dimensional setting, it doesn't matter which model one uses, one gets the same. So the sets of quantum correlations are the same. So QS and QC are the same when only finite dimensional Hilbert spaces are being used. Now, there is a more traditional notation that people in quantum information and working in this area are using. So for the finite dimensional setting, the two sets which are the same are additionally denoted by C, script C sub Q. and I'll use that notation from now on. And the closure of CQS, it's denoted by CQA, A maybe from approximable, I think. And what I want to explain on the next slide is that if you want to obtain the closure of CQS, it's enough to look at the finite dimensional setting and take the closure there. So that's an interesting thing. And in order to explain that, I will tell you that was the moment when groups and analysis of their sister algebras came into play. That was around 2009 in work of Tobias Fritz, respectively independently of Marius Junge and collaborators, when they were using this group gamma, which I denoted here by f of n comma k. So this is the free group on n generators, each of them with of order k. So this is a free group of n factors of z mod k. The sister algebra of this group, it's very easy to understand. I don't intend to read this description of sister gamma. It was only meant to bring into play these projections q sub I comma x that are in the statement of the following theorem. But I'm not going to read the statement in all of its details. I'm just restricting myself to telling you that this theorem, due independently to Tobias Fritz and Marius Junge and collaborators, shows that one can understand or express the set of quantum approximable CQA correlations by looking at the state space of this sister algebra, the mean tensor product of sister gamma with itself. Respectively, one can describe the set of quantum commuting correlations by the state space of the max tensor product of sister gamma with itself. Now, the state space of any sister algebra is closed in the weak star topology, leading immediately to the conclusion that the set CQC is closed. And I will also be able to explain now why I told you that to take the closure of CQS, the quantum in the spatial tensor product model, it suffices to consider finite dimensional spaces for producing these correlations and taking the closure there. A nice explanation for that we can now give here, using the fact that the property of being RFD, it's closed under min tensor products, and sister gamma is RFD, therefore min tensor product of sister gamma with itself is RFD. And another nice result of excellent Loring shows that if a sister algebra is RFD, then the states factoring through finite dimensional sister algebras, the states on A factoring through finite dimensional sister algebras are dense in all the state space of A. So in view of the theorem of Fritz, respectively, Junge and collaborators, we have this now. I think it's a nice operator algebraic way of looking at things. So now is the diagram again, with all these explanations having been given. Right, and I am now going to say that indeed there are more correlations arising in the quantum world than in the classical one. This is a statement of Bell's inequalities holding, but from a functional analyst perspective, this also follows from the fact that the universal constant in Grothendieck's theorem from function analysis is strictly larger than 1. That is responsible for the separation between classical and quantum sets of correlations. So coming back to Cyrilson, his result from the 80s that when only finite dimensional Hilbert spaces are concerned, one gets the same sets of quantum correlations, whether using the spatial or the commutativity of observables model. He conjectured that this holds true regardless of Hilbert spaces or other dimensions. So also when infinite dimensional Hilbert spaces are being used, Later on, he realized that there may be a problem with his reasoning, and that became the so-called Tyrrellson problem. And so formulated here as following: is it the case that the closure of CQS is equal to CQC always? So CQC is always closed. And as I said, it's not clear if CQS is always closed. So the closure of that, is that equal to CQC? So the infinite dimensional version of his result from the finite dimensional setup. And the breakthrough in discussing or making progress in Tyrrellson's problem came from work of William Slofstra in 2016. He showed that the two sets, CQS and CQC, are different. So it does matter which model one uses in the quantum infinite dimensional setting. And furthermore, in 17, he could show that CQS is indeed not closed for n and k large. It's a very solid piece of mathematics using a lot of group theory, for example. And so 2017, Dijkema, Paulsen, Prakash took it down to 5,2. So CQS is not closed in dimensions 5,2, so 2 is k here. And as I already explained, we recasted their result in staying completely within operator theory framework, and used these results for settling other questions as well. So now for my last two slides, the remaining time, I hope I have it. I'd like to discuss some very recent progress or developments in the analysis of quantum correlations, most prominently the class of synchronous ones, and yeah, the so-called Connes-Kirchberg problem. So the notion of synchronicity for a correlation was introduced by Paulsen in 2016 in work with his collaborators, Stolke, Severini, Ivan Todorov, and Andreas Winter. And so they call correlation to be synchronous if it satisfies the following condition, namely that the probability that Alice and Bob obtain different outcomes when measuring the same input is 0. So probability of I, j, where I is different from j, given x, x, so same observable but different measurements for that is 0. So such a correlation is called synchronous. And in a very nice result that they proved is that they can interpret or characterize the correlations in the quantum commuting model, which are moreover synchronous. So it's an intersection with the synchronous ones, respectively. The correlations in the quantum finite dimensional setting, which are moreover synchronous, using the tracial simplex of the C-star algebra of this free group of n generators, each of them of order k, respectively using T-fin, the tracial states which factor through finite dimensional C-star algebras on C-star of this group. So that's a very nice result. And now you may recognize here a result in the same spirit as the one I showed you before about trying to understand the closure of T-fin before it was for the free product of Mn with itself, 2 copies of Mn. So here is for the C-star algebra of this group freely generated by n elements, each of them of order k. This is a result that Chris Schaffhauser showed at an AAM meeting in 2021. And I'd like to bring it here because it illustrates somehow the same techniques of the proof, but also I'll be able to build on it further. So what he showed is that if you look at the closure of T-fin of the C-star algebra of this free group, you get all the way to the hyperlinear traces on this C-star algebra, very much same spirit as before. And in particular, using this, one can show that if Connes embedding is true, then since all traces are hyperlinear, then the closure of T-fin, it's all tracial states on here, on C star of this free group. But in fact, using the same ideas as before, the ideas that Jesse suggested to us, one can show that this is an if and only if result. So Connes embedding is true if and only if all traces on C star of F and comma K are limits of traces that are finite dimensional traces. So traces that factor to something finite dimensional. Now, so I don't want to comment on the proof, but I'd like to show you another very beautiful result of Chris Schaffhauser together with Vern Paulsen and Kim from 2018 that shows that, in fact, the operation of taking or restricting to synchronous correlation commutes with the operation of closure. So for all n comma k greater or equal to 2, the closure of CQS is equal to CQA, the approximable ones, synchronous. So the closure passes, commutes with synchronous, so passes, inside. Now, this is actually a very solid piece of operator algebra results. So it uses some of Kirchberg's results on amenable traces. And maybe the novelty that I want to bring here, so some recent developments, is that there is a new proof of this result using a notion of almost synchronicity for quantum correlations that was introduced and studied by Thomas Vidic in a paper in 2022, where he obtains a new proof of Kim Paulsen-Schaffhauser result. And also there are new developments, namely an extension of Thomas Vidic's result in the infinite dimensional case due to, and I have the banner on the bottom, so I'm reading what I think it should be written there. So it's a result of Michael de la Salle with Amin Marakchi. I think it was posted also late July on the archive, so very recent. And also there is another independent new proof using this notion of almost synchronicity due to Jinqiao Lin. I think it's his master's thesis. Maybe William will correct me if I'm wrong. From 2023, maybe late spring 2023. He is actually visiting Copenhagen right now. So I look much forward to discussing more with him about all of these things. So now this is my last slide I have, where I'll show you this grand finale theorem with the fundamental contribution of Eberhard Kirchberg to the study of the Connes embedding problem. So he proved that Connes embedding problem has a positive answer if and only if there is a unique C-star tensor norm on C-star F infinity with itself. This via the connection to Zirelson's conjecture led to a settling, so having all these three assertments being equivalent with the additional work of Takaozawa, which connects, I think, 3 implies 1 in this theorem. So this is a fundamental result due to a lot of work of many people. So Connes embedding problem has a positive answer if and only if Zirelson's conjecture is true, namely the closure of CQS is equal to CQC for all n, n and k greater or equal to 2. This going via Kirchberg's reformulation or equivalent formulation of Connes embedding problem using uniqueness of C-star tensor norm on C-star F infinity with itself. And as we all know, I think in January 2020, G. Natarajan, Tomavidik, John Wright, and Eric Yuen announced on the archive that MIP star is equal to RE. So unraveling in more words what this means, proving that the complexity class MIP star contains an undecidable language. They concluded that Zirelson's conjecture is false. Therefore, Connes embedding problem has a negative answer. So I want to maybe put in writing this last statement that this fundamental work of them or extremely interesting work of them and its further versions have led to highly interesting interconnections between operator algebras and groups, quantum information theory, complexity theory in computer science, including topics such stability of groups, non-local games, self-testing, and so on, many of which are, objects of current study, and so very, very, very interesting interconnections. And I'm sure that you have heard or are going to hear a lot more at the conference about all of this. So with this, I think I'd like to end my talk, and thank you.